Hello and welcome to Calculus Tutorial. We are going to keep taking a look at implicit differentiation. But now that we can do that skill, we want to try to apply it. So how do we apply this implicit differentiation? Well, it's this thing called related rates. And what we're going to do is we're going to take some geometric equations, so in this case spheres and cylinders, and we're going to apply implicit differentiation to them. So, geometric equations. We're going to start with a nice easy one. Imagine a cylinder that is being inflated or deflated. A great way to think about this is microwaving a marshmallow. If you've never done that before, pause the video and go do it. It's amazing. But when you microwave a marshmallow, the marshmallow just expands. It gets bigger, and so the volume also gets bigger. And so if you think about the equation for the volume of a cylinder, it is pi r squared times the height. And then when you type in, say, 10 seconds on your microwave and hit start, the radius gets bigger, the height gets bigger, and the volume gets bigger. They all change as that timer is ticking down. So we've got three variables, v, r, and h. And as time goes by, they all change. So the volume changes with respect to time. The radius changes with respect to time. And the height changes with respect to time. So you can see we actually have four variables, v, r, h, but also t, because you hit 10 seconds on that microwave and hit start. So time is also working here as well. So what is the relationship between these? What is dv dt, what is dr dt, and what is dh dt? To figure that out, we're going to take this equation and take the derivative implicitly. So we're going to take the derivative with respect to time of the left and the derivative with respect to time of the right. So let me put the equation in there. So this side is just v. And on the other side we have pi r squared times height. So the left side is our easy side this time. What is the derivative of v with respect to t? Well, that is just dv dt. Is equal to. Now, if I take the derivative of this, that gets a little complicated. As you can see, I have a variable times a variable. That is going to require the product rule. So I'm going to call this the first and this the second. Okay? So take the derivative of the first, so the 2 multiplies down. Oops, not squared anymore, is it? So we have 2 pi r, but do you see the variables don't match? So we have to add a dr dt. So we took the derivative of the first, and the product rule says now I have to multiply by the second, which is h. No derivative for that second, remember. Plus the derivative of the second. So what is the derivative of h? Well, that's 1, but the variables don't match, so we add a dh dt times the first, which is pi r squared. And there's not much we can do with this equation. Yes, we could reorder these. You might want to put this h over in front of the dr dt. You don't really need the 1, and you can put this in front. So I suppose I could rewrite this. It's not going to change much. So I might go 2 pi r h, and then the derivative. plus, don't need the 1 pi r squared times dH dt. And so now we have an equation that relates all the rates, hence the name related rates. All right, all of these rates of change are related to each other, and this is the equation that shows how they are related. Related rates. So when you hit that button to start the microwave, the volume changes, the radius changes, and the height changes, and they're all related to each other. All right, so now that we have an idea of how to use implicit differentiation on a volume formula, let's actually put some numbers in here and try this out. So we're going to focus on two different geometric formulas, spheres and cylinders. Let's keep doing cylinders since we got some practice there already. So, yes, it's a word problem. Stay with me though. So a winery uses giant cylinders to store its wine. These tanks happen to be 20 feet in diameter and 30 feet tall. The wine from one tank is being drained, and the height of the wine is falling at 0.5 feet per hour. How fast is the volume decreasing? So, one strategy I have for you here, list out the formula. Volume is equal to pi r squared times the height. Then, look at all your variables. We have v, we have r, and we have h. And then we have dv dt, we have dr dt, and we have dh dt. We know we want to take the derivative, so we may as well take the derivative of our formula. So on the left we have the derivative of v with respect to t, and on the right we have the derivative of pi r squared times height over dt. Let's practice this one more time because it is fairly complicated. So the left is going to stay dv dt. So now over here we have to do the product rule. So the derivative of the first times the second plus the derivative of the second times the first. So the derivative of the first is 2 pi r, but the variables don't match, so dr dt times the second. That's the hard one. You did all that work to find the derivative of the first. Don't forget to multiply by the second, plus the derivative of the second, which is just 1, but the variables don't match, times the first. All right, so we have our derivative here. Now we need to plug things in. So let's fill in what we know about this problem. Let's see. It is 30 feet tall, so that's the height. It's 20 feet in diameter, which means the radius is only 10. Do we know the volume? Didn't give it to us. Let's see. The wine from one tank is being drained, and the height of the wine is falling at 0.5 feet per hour. So hopefully you can translate into that. That is how fast the height is changing. Well, that's dH dt. So dH dt is negative 0.5. It's falling negative 0.5 feet every hour. Now there's one more piece of information here that, how fast is the volume decreasing? Well, we want to find dV dt. How fast is the volume changing? So wouldn't it be nice if we knew what dr dt is? That's also in our equation. Well, we do. Think about this tank here. Here's the cylinder. As this wine falls, what do you notice about the radius? This radius, this radius, this radius. Hopefully you can see that the radius is not changing, all right? The sides of this tank are not getting bigger or smaller, whereas the sides of your marshmallow definitely do get bigger and smaller. So the radius is not changing, which means dr dt is 0. It's not changing. Now that makes this problem much, much easier, and later on you'll do that step first. Sorry. But think about that. If dr dt is 0, 0 times all of this right here cancels out. So because the radius was not changing, all that cancels out. So we're just left with dv dt, which is what we're trying to find, is equal to dh dt, which we know is negative 0.5, times pi, times r squared. Well, we know what r is. It is 10. So, there we have it. All of our variables have been taken away. We just have dv dt, which is what we are trying to find, which now will be equal to, we can do this in our head, can't we? 10 squared is 100, times a half is 50, so negative 50 pi, negative 50 pi. If you want to turn that into a decimal, it'll be like 150, 160, something like that. Not super necessary. But we need some units. What are our units? Well, it's volume per time unit. So our volume will be in cubic feet. Cubic feet. And we're measuring this in hour, so per hour. So about 150 cubic feet every hour are draining out of this tank, and that will make the height fall at half a foot per hour. All right, so we used the rate of the radius falling to find how fast the volume was falling. So that's cylinders. Let's do one more. Let's do spheres. And I gotta tell you, spheres are much easier. It's kind of nice. I'll erase that as well. Spheres are much, much easier, and you'll see why here in a second. So Rachel is blowing up a balloon so that the diameter increases at a rate of 10 centimeters per second. At what rate must she blow air into the balloon when the diameter measures 4 centimeters? So if you want to think about a balloon, we're going to approximate it as a sphere. Here's my best sphere for you, sorry. So what variables do we have here? Well, the volume of a sphere, if you'll remember, 4/3 pi r cubed. So when we take our volume formula and list out our variables, we only have v and r. Is the volume changing? Yes, it is. dv dt. Is the radius changing as you blow up the balloon? Yes, it is. You have dr dt. So this one's going to be easier because we have fewer variables. We only have v and r. This one's going to be quite a bit easier. So when I take the derivative of both sides, I'm going to have the derivative of v on the left and the derivative of 4/3 pi dr cubed on the right. And so this one's much easier because this does not require a product rule. We only have one variable over here on the right side. So it's just a simple power rule. 3 is going to multiply down and actually cancel out the bottom 3. So we're just going to be left with 4 pi r squared. Now again, the variables don't match. So we have dr dt is equal to dv dt. So our derivative was much easier because we didn't have a product rule. All right, but we can substitute some things in. What do we know? All right, the diameter increases at a rate of 10 centimeters per second. All right, couple of things there. If the diameter is increasing at 10 centimeters a second, that means the radius is increasing at 5 centimeters a second. The radius is half of the diameter. At what rate must you blow air into the balloon? When the diameter measures 4 centimeters. And so if the diameter is 4 centimeters, the radius is only 2. Now we don't know what v is, but thankfully there's no v in the equation. We don't know what dv dt is because that is what we are trying to find. So now we simply plug everything in. dv dt is equal to 4 pi. The radius is 2, so that is 2 squared, times dr dt, which is 5. And then however you want your answer to look, let's see, that's 4 times 5 is 20, times 4 is 80 pi. 80 pi what? What are our units here? We are measured in centimeters and seconds. And so if this is volume, that will be cubic centimeters. There's a nice easier way to write it. Every second. And if you don't like the pi, you can multiply that by pi and actually get a decimal. It'll be what? Something around 240, 250 cubic centimeters per second. But that is the rate of the volume that must be in order to have the rate of the radius be 5, or in this case, the diameter being 10 centimeters per second. Those two rates are related, so if you know one, you can find the other. All right, that is a quick look at related rates. Hopefully that helps clear some things up.